A cyclic process. 3 moles of an ideal gas are taken around cycle ACB shown in figure. So you can see we start with constant pressure, then we have the process from C to B and B to A is at constant volume. Process A to C is at constant pressure. Process B to A is at constant volume, and process C to B we learn is adiabatic process. The temperatures of the gas in states A, C, and B are 300 Kelvin, 492 Kelvin, and 600 Kelvin. 300, 492, 600. Calculate the total work for the cycle. Now I want to start out by writing the ideal gas law at point A. We have pressure at point A, volume at point A is equal to 3 moles or 300 Kelvin. And then if we write point A, pressure at point C is equal to pressure at point A. So pressure at point A, volume at point C is 3R 492 Kelvin. So here I have noted PC is equal to PA because it's isobaric process. If I take the ratio of these two equations, I would obtain the pressures cancelling and the 3 R's cancel as well. So I will be left with the ratio of the volumes, the volume at point A divided by the volume at point C is 300 over 492. So this tells us that the volume at point C is 1.64 volume at point A. So the process involves going from VA to 1.64 VA and back to the original volume VA. Whether or not this will be useful, I don't know, but at this point I want to determine how the volume changes using this information. Now, in order to calculate the work done for this cycle, let me first think about the heat added. The heat added between point A and point C, which is a constant pressure process, is NCP delta T. The number of moles is 3, and the CP value is given for this gas, 29.1 joules per mole Kelvin. So it's 29.1 multiplied with the temperature difference, 492 minus 300. This is 16,761.6 joules. That's what I find. The heat added to this gas between point C and point B is 0 joules. Why? Because it's adiabatic process. Adiabatic by definition means there is no heat exchange. At the same time, I know that always Cp minus Cv is equal to the universal gas constant R. So I can calculate Cv as Cp minus R. So it is 29.1 minus 8.315. So Cv value for this gas is 20.785 joules per mole Kelvin. So the heat added between point B and point A, and remember that part is isovolumetric, is NCV delta T because it's isovolumetric. So it's 3 times 20.875 times the temperature change. We're going from 600 Kelvin to 300 Kelvin. So this is 300 minus 600. So the heat added to the gas between point B and point A in the isovolumetric process is minus 18,706.5 joules. What is the total internal energy change? The initial state is A Final state is A. Internal energy is a state variable. The internal energy change for the cycle is 0 joules. Therefore, heat added from point A to C, C to B, and B to A is going to be A to C, C to B, and B to A, back to A, will be 16,761.6 minus 18,706.5 plus the work done for this process starting from A, C, B, A. So again, A, C, B, back to A for the full cycle. That's what I'm trying to determine, plus W. This has to be equal to 0. So the work done for the cycle must be equal to 1944.9 joules. Now, how many significant figures do I want? I want 3 significant figures. So I will reduce it to 1940 joules. And what is this? This is work done on the gas. Work done on the gas. Okay. So if you follow the right-hand rule, if you follow the process, it's actually counterclockwise process and your thumb points out of the board. It's also telling you work done on the gas must be positive. So to summarize, I was asked to calculate the total work done for a cycle, knowing that the process consists of 3 steps: isobaric, adiabatic, isovolumetric. If I calculate the heat added to the gas throughout the cycle, because the internal energy change for the cycle has to be 0, I can calculate the work done. First, I have determined these volumes at point A and C, but I don't really need that. But it's an information I can obtain from ideal gas law, because it's an ideal gas. And to calculate the heat added between A to C, isobaric process, it's NCP delta T. C to B is adiabatic, 0, and B to A is isovolumetric, NCV delta T, and I'm given CP. CP minus CV is R, so I can calculate CV and substitute. And if I calculate the total heat added to the gas plus the work done on the gas, this must add up to 0. So from this, I can obtain the work done on the gas.